In this video, we are considering linear regression. This is the first part of a short series of videos. Just to remind, the task of supervised learning is divided onto two divisions. Regression, where we are predicting continuous values of some variables or parameters, and classification, when we want to classify some object into a particular class based on some features. So, regression is a technique for predicting a continuous value. For example, we have some set of features, X, and training targets, Y. We must the learning algorithm to be trained so that it would classify new features X, which did not take part in the training process, as is shown on this diagram. So we want to find some function f, which is linear in regard to the feature x. First, we consider the simple case of univariable regression when we have only one feature. Like, for example, on this graph, we have feature x and variable target variable y. And we want to make a prediction of y based on x. For example, this linear prediction, this line of y depending on x could be like shown here on the right. So again, we are trying to make such a prediction or approximation y hat, which linearly depends on feature x. Wx plus b is usual form to make a linear prediction based on input parameter, input feature x. The geometrical sense of the parameter y, or weight coefficient y, it's a tangent of an angle which makes the line of linear prediction with the axis x. So the tangent on this angle is weight w. And b, also called sometimes intercept or bias, is some deviation from the origin point 0, 0. So if b is equal to 0, this line would go exactly through the origin, to the point 0, 0. Let's consider an example of a data set describing the characteristics of the cars, so-called car small data set. There are several parameters here in this data set, and we consider the prediction of miles per gallon, the parameter characterizing the fuel consumption of the vehicle. It would be a target variable y based on feature x, which is in this situation the weight of the car. The particular data present in this dataset are shown, some part of them is shown on this slide. So we can plot the variables x, the x and y on the same graph. Well, it could be seen they are not exactly linearly, but there is some dependence quite close to linear between them. Now the task is to select particular w and b so that we would have as good as possible approximation of our labels y based on features x. So miles per gallon based on car weight. Yes, some particular choices for this are shown here. Let me go to the collab, and I will load this data x and y. Here I plot them. I plot them exactly as you have just seen on the slide. We convert using the NumPy library. We are converting the x and y to NumPy arrays. And we can see, by the way, different characteristics of arrays X and Y. For example, the mean, or for example, maximum value, or mean value, or minimum value, etc. So, yes, we can set different possible choices of Y and B and see how it would result into the potential approximation of Y based on X. Like here also, I show here the approximation error, root mean square error based on training data. We did not yet divide the data into training and testing, so it's just this RMS error for the whole data set, 4.3. I also prepared some kind of slider in Python for the same data set. Here we can see how varying of parameter W results into the form of this linear approximation, and correspondingly we can move the parameter B as well. And also here you can see that root mean square error in the right upper corner of this graph differs correspondingly. So we must endeavor to find such parameters W and B which approximate as close as possible our data points. So for example, I'm here, you can see that the error reduces from up to 4.14. Yes, it could be very close to the desired W and B. So let us come back to our presentation. Yes, and we want to find the optimal approximation, which would produce this error 4.1. We can do it, of course, manually, but it's could be quite difficult. So first of all, as in all learning algorithms, we must divide our data into the training and test data. So the goal is to construct in machine learning, generally, the goal is to construct the algorithms which models that generalize. They perform well on never before seen data. So we must train our model on some part of the data and test it correspondingly on the independent subset. Yes, because if we can achieve very good result on some part of training data, but it will not work at all, it would be totally unfit on another set of data of the same kind. So that is why, again, we're dividing the data onto the training and test parts. In more general case, about which we are talking in another video about validation, is to subdivide further training data into the training data and training data themselves and cross-validation data. But here we just consider a smaller example of just considering training data and test data. So let us prepare our data, training and testing, and for this purpose we can use a specific function from sklearn library. It's called train test split, a very useful and convenient function which splits our sets X and Y onto the subparts train and test subparts correspondingly. We can set here the percentage of the test data and also some randomization parameter which would arrange the random subdivision of our initial data set onto these two subsets. Again, we have to have a train data set for training and data set for testing. Also, I would like to mention one important moment that very often, and also in particular in our example, data should be scaled to have the same range, because we can see that here X and Y have completely different ranges. X is something about from 2000 to 5000, and Y is just from 10 to 14. So it's instructive and very useful to make scaling of our data. It's important in many different kinds of machine learning problems. So if we're making this scaling, now you can see that X and Y now have the same range of values, approximately from -2 to 2. So what is the principle of this scaling? The principle of this scaling is to extract mean value from our parameters features X, and also mean value from labels Y, and then dividing them by standard deviation sigma. So X is now X minus mu X divided by sigma X, and correspondingly Y, variables Y, target variables Y are similarly scaled. This can be done with a simple Python function as is shown here. Yes, we are calculating mean value, we are subtracting mean value, and then divided by sigma, standard deviation. And it results that our data are now looking in this way. Here, it does not have much physical meaning now for us, but nevertheless, these data are very useful for the very convenient for subsequent processing, and I will show the reason why. So one important moment, we have now training data, we have labels Y, we have to define optimality criterion. So-called loss function between our predictions and factual values of target variable Y. So what is the natural choice for linear regression? It's a mean square error, like shown on this slide, between Y and Wx plus B. Average or mean square error. And so also we see here the graph of this function, and you can see that it's convex. It's very nice feature is that it's convex and correspondingly it's unimodal. Unimodal means that it has only one point of minimum. The local minimum here coincides with the global minimum, which is very convenient. So we know that our solution for this problem has there is only one solution for this minimization problem. What I want to mention that it's very important for data to be scaled, because here we also see that what would occur that if our data are not scaled. So the cost function would have the form which would be more difficult to minimize. Yes, and some insignificant errors would be it will be very sensitive, yes, to some errors in our calculations. But when the data are scaled, it's definitely convex. It's definitely convex and has a very nice form shown on the right. And that is why the data should be preliminary scaled. So once we have defined this function, it's called cost function. Cost function means it's the error is averaged over the whole training data set. And now natural way to find the minimum of the convex function is to compute its derivatives of cost function j, to compute the derivatives, and taking the derivatives by weight W and by bias B. Corresponding derivatives, skipping the constant factor of 2, are shown here on the right. And we force them to be 0 And from these equations, they become, we can derive from here linear equations for W and B, and we can calculate them in the following way: y hat and b hat. So it's closed form or analytical solution for this problem. And for our particular example, we get corresponding W of minus 0.0086 and B of 49.24, which results in the corresponding error for the whole data set. Later, I will show what is the error particularly for training, separately for training and test data set. For this purpose, let us go to Colab again, and here these corresponding formulas. And I have just programmed this formulas in Python. Let me see if I've set the data to be scaled. Yes, now they are scaled. The data are scaled, and I can calculate W and B by the following forms. But the very nice property of operating with scale data. When we operate with scale data, our formulas, these formulas, let me show them again. They greatly simplify. They are greatly simplified. In the case when data are scaled, when they're centered and scaled as we shown before. Let me see. It's like is shown here. The formulas become like just like this. W like dot product, mean dot product of x and y, and b will be 0, which is quite natural because the data were centered. Yes, so we can calculate this w and b, but in the case we performed scaling, there should be inverse transformation to come to the w and b for the original non-scale data. For the original non-scale data, we must calculate w and b. So the answer that we get is minus 0.008 and 48.6. So we perform this calculation using scale data and then turning back to the returning back to the for the parameters WB for the unscale data. By the way, here I believe, yes, here the approximation, linear approximation is shown. Here separately are shown the data for training and test data set. I believe in blue it's for train, and in green points are for the test data set. And we also have this y, this red line y is for the testing data points. X multiply W multiply X test plus B. So, and we have root mean square error for the root mean square error 3.8 for training data, and it's lower than the error for test data, which is quite natural. This would not always be the case, but nevertheless here it's quite natural that the error for training data is less than the error for test data. So, and again, here is a graph for the cost function, the graph for the cost function, and something is missing. Okay, I will run again the whole. Maybe I missed some of the cells in this Colab document. Yes, when the data scale, the cost function has a very nice form, and we can also analytically find this point of minimum. And again, we have a W and P shown here. Where are they? Yes, parameters for the unscaled, yes. These are parameters for scaled model, where b is equal to 0, and parameters for unscaled model, minus 0.008 and 84.6. Now let me perform the same calculations using the data which were not scaled. Well, just to check that our formulas are correct. Where is this flag, which I now require the data not to be scaled. Well, I don't run the whole script. So data, as you see now, again, are not scaled. They're not scaled, but we get the same result. We get the same result for W and B. And the same root mean square error for training and taste data set. Yes. But in this case, the cost function looks a little different, as you can see here. Yes, and of course, in this case, we get the answer anyway. But it's what I wanted to stress in this video, that also, in particular in this video, this data should be scaled so that the cost function would have a nice form suitable for minimization. Yes, it will be especially instructive for other more difficult machine learning problems. So I think that's all what I wanted to explain in this video. In the next video, we will continue, starting with the gradient descent. Thank you. Thank you very much for your attention.